Add the other worksheet.
What's that?
Add the worksheet.
Okay. All right, so let's go ahead and solve these two, and then we have a second worksheet, and then we'll do some problems with capacitors. I was also told that SpaceX is doing a launch at 3, right? Yeah. So I'll try to find a link for that so we can watch that too, and then because we're taking time to watch YouTube, I expect everybody to write a page paper on the kinematics of rockets, and I'm just kidding. I'm just kidding. But you could. We knew how to do that from last semester. Okay. So for the first circuit, we wanted to do this using the series and parallel method. So first, let's go ahead and draw what this circuit looks like. Okay, so this was 3 ohms, 9 ohms, 9 ohms, 6 ohms, 6 ohms. This is the circuit of the beast on the outside here. So this is 24 volts. Okay, so the first thing that we want to do is to find what the equivalent resistance of this circuit is. And the way that I'm going to do this is I'm going to draw it step by step so you can see what it is that I'm doing as I'm collapsing this circuit down to one resistor. So the first thing that I'm going to do is I'm going to combine these 3 together because they're in series, and these 2 because they're in series. So what that's going to look like is this. So I'm going to rotate this a little bit now. So this is what the circuit looks like after I collapse those 2 to some equivalent resistances. So what's this resistance on the outside that would be the sum of these in series? 18, right? So this is 18 ohms. And how about this one? 18. So this one is still the 3. So the next thing that we want to do is to take this and then combine these 2 that are in parallel. And so when I do that, this ends up being like this. So this is still our 3 ohms. And then what's this one? This is 9, right? We can see why this is 9, because when I add these in parallel, what that means is I do 1 over 18 plus 1 over 18 to the -1. So this ends up being 2 divided by 18, which is a 9th. Inverted gives me 9 ohms. So then the last thing that I do is I add these 2 in series, and so that just means we're directly adding them together to get this one. And so this ends up being 12 ohms, and then this is our 24 volts. Okay, so then when I want to find what the current is here, that's just to say that V is equal to IR, or I is going to be equal to 24 divided by 12, which is equal to 2 amps. Okay, so those are the first 2 answers. That's the total resistance and the total current. Now, when we look at this, I can define these currents. So I have some I1 going here, some I2 going here, some I3 going here. So I can say that whatever is going in is equal to what's going out. And so I1 is equal to I2 plus I3. And I noticed something really interesting here. This resistance is the same as this resistance, which means that the current is going to split equally between these 2. And so because this is 2 amps going in, this ends up being 1 amp and 1 amp. So our currents for this whole part here, this is 1 amp. So this is the 2 amps, and this is 1 amp. Okay. The current down here is also 2 amps, right? Because those 2 paths come back together to combine. And so then the last thing that we want to do is just find what the change in potential is across these. And that's, again, just to apply V is equal to IR. So if I want to find what the voltage across this one, I take the current and multiply it by the resistance. Same thing for all of them. So once we find the current everywhere, it's pretty straightforward to find what the the voltage is across each one. Okay. So the next one, was there a question?
Can you leave it?
Yeah, sure. Did I erase something that you needed? Okay, what did I have there? This was 12 ohms. This was like the middle of what I was saying.
24 divided by 12.
Okay, yeah. So this is I is equal to V divided by R, which is equal to 24 divided by 12, which is equal to 2 amps. Okay, yeah, that's what I erased. Okay. So the next one, we asked you to do using the loop rule. So let's draw this. And I changed what some of the values of the resistors are here so that it ended up being a little bit easier to do. So this was 2 ohms, this was 6 ohms, this was 24 volts, this was 12 ohms, this is 6 ohms, 6 ohms, and 3 ohms, and 3 ohms. Okay, so when we want to apply our loop rules, the first thing that we can do is we can define the junction. So I'm going to use this point here and say that there's some I1 going here, and this is going to split to some I2 and some I3. Okay, so I1 is going to be equal to I2 plus I3. Now the next thing that we want to do is we want to draw some loops. Now you had some choices here. The ones that I chose to do were this one. So this one, I'll call this, let's call it loop A. So I'm not using my same capital I's. And then this one, call this loop B. So when you do this on the test, when I taught this at Texas A&M, we had some very strict rules about this, which turned out not to be so strict because people that did this ended up getting the right answer. But those rules were, if you don't label your currents and you don't label the direction of your loops, we're not even going to grade it. For the sake of my sanity and the sanity of the graders, I think they'd probably agree that that's a reasonable policy, because you end up having so many different negative signs that you can get if you don't define things and tell us what it is that you're doing. So I'm probably not going to be able to convince them to institute that policy, but what I will say is if you want the graders to be patient and happy with you, make sure that you're drawing all of the directions of your currents and the direction that you're going around in the loop. Okay, it'll help you get the right answer. So for this loop A, what I end up seeing is I'm going around this loop, I'm dropping in potential going this way, and so this is going to be a minus I3 times the sum of these two resistances, which is going to be 12 ohms. And then I'm going around this way again, and now I'm increasing in potential going this way. So this is going to be a plus I2 times, again, the sum of these resistances, which is going to be 6 ohms. And from this, I can simplify this in order to show the ratio between I2 and I3, and this is equal to 0. So that ratio is going to be that I2 is going to be equal to I3 divided by 2, right? So I move this to the other side and then I divide by 6. This should be the other way around. This should be 2 times. Okay. This is a little bit different than the way that I reversed my notation when I did this on my paper, that's why. Okay, so now the second loop that we're going to do here, this is going to be an increase in potential starting here, so this is going to be plus 24 volts, and then I'm going to get a minus 12 ohms times I1. Now I'm coming down here, this is going across I3, but this is going to be going across both of these, so I can combine that resistance. Sorry, this is I2. So this is going to be minus 6 times I2. And then I get down to here, and I'm going across this one. This is going to be a total resistance of 8 across here, and this is the same I1 that I had, and it's going to be a decrease in potential. So this is minus I1 times 8 is equal to 0. Now I can combine this and this so that I can simplify my equation. So 24 volts is 24 volts minus 20 times I1 minus 6 times I2 is equal to 0. Okay. Now, in order to get this equation down here, only in terms of I1, what I'm going to do is I'm going to take this equation and I'm going to plug it into this equation here. And actually, the way that I'm going to do that is I'm going to say that I3 is equal to I2 divided by 2, and take this and plug it in here. So that when I do that, I'm going to have a ratio for I1 and I2. So this is going to say that I1 is equal to I2 plus I2 divided by 2, which says that I1 is equal to 3/2 times I2. Okay? So now I have I1 is equal to 3/2 I2. I can take this one now. It's a good time to use some colored chalk. This one and take this, and I can plug it into here. Okay. So when I do that, what I end up having is 24 volts minus 3/2 times 20 is 30, so this is 36 times I2 minus, I combine that too. So this is 30 I2 minus 6 I2 is equal to 0, which means this is 24 volts minus the 36 I2 is equal to 0, or I2 is going to be equal to 24 divided by 36, which is, this is 4/6, this is 2/3, so this is equal to 2/3. Okay? So then what I can do is I can take this, now I can plug it back into this equation, and that says that 3/2 times 2/3 is equal to I1, and so I1 is equal to 1 amp. There's questions? Yeah.
So, in your A loop, how do you know, basically, how do you know whenever something is positive in your loop or when something's negative?
Sure. So there was something that I didn't draw here, and that's the polarity across the resistors. And so this is plus, minus, plus, minus, plus, minus, plus, minus. And so when I'm going around this loop, I'm going from plus to minus. So that's a drop in potential, which is why this one is going to be negative here, right? And then I'm going around this way, and I'm going from negative to positive.
So that plus minus is based off the current that's going, which way the current's going?
Right. So current flows from positive to negative. Same way electric field goes from positive to negative. Yeah. So then the last part that I need to do here is to find what I3 is, and I3 is just going to be I2 divided by 2, and so what that says is that I3 is equal to 1/3 of an amp. Okay. Yeah.
Which way do you define as I2?
I2 is the one that's down here. Sorry, it combined with my 3 ohms.
No, it's fine. It was really small?
Yeah, I'll try to write bigger for you guys in the back. Other questions? Now, the thing about these loop kind of equations is that there's a lot of different loops that you can choose. There's a lot of different directions you can choose. And then the algebra is always going to be a little bit different depending on what your choice was. But the important thing is that you're consistent in the way that you define what the direction of your current is and the direction that loops are going, and then use that when you build the equations. So if this was an exam question and say it was out of 20 points, 15 of those 20 points about would have been drawing these loops, drawing the currents, and writing down these three equations. So it might only be like 5 points for doing the algebra. Okay. Any other questions about this? Okay, so we have a second worksheet that I'll pass out, and we'll work on this for maybe about 15 minutes, and then I'll let you guys take it home and work on it some more for practice. Okay, so we're gonna actually move on from here because I don't want to spend too much more time on resistors, but you guys can work on this at home, and you have what the answers should be. So this is good practice. So the next thing that I want to do is I want to talk about capacitors. So we talked about resistors and what they do in circuits. So resistors, in a sense, they dissipate potential, and you can say in a sense the same thing when you're applying Kirchhoff's rules to capacitors. But really what capacitors do is they store energy, right? And the one way that you can actually see that is if you look at what the potential energy of a capacitor is. The potential energy of a capacitor is 1/2 Q squared over C. Now, does that look a little bit like something we've seen before? We had 1/2, and then we had something squared. Do we remember something from last semester that had a potential energy that had a 1/2 and then something squared? A spring, right? So a spring potential energy looks like 1/2 kx squared. The capacitor potential energy is 1/2 q squared divided by c. And so if we think about that analog between springs and capacitors, in a mechanical system, the spring is something that stores energy, right? I compress it and it's holding energy. Well, when I put a bunch of charge on a capacitor, it's doing the same thing. It's storing energy that can be used later. And so when we talk about capacitors, we can do the same sort of circuit analysis that we do with resistors, where we can add them in series and parallel. So if I had a capacitor in series, it's going to add a little bit differently than it does for a resistor. So these relationships actually flip when I talk about adding things for capacitors. So in series, when I add capacitors, this is going to be 1 over CEQ is equal to 1 over C1 plus 1 over C2. And when I add them in parallel, this is going to be CEQ is equal to C1 plus C2, okay? So to get us to think more about capacitors, I have a couple of, I'm going to move this to the side, but I won't forget it. I have a couple of slides that I stole from Dr. Marius because I'm apparently incapable of pressing Control S when I make my own slides. So the first thing that we want to do is we want to find what the units of capacitance are based off of this equation here. So the relationship between voltage and capacitance and charge says that the charge that's on a capacitor is going to be equal to the voltage across the capacitor times the capacitance. And so what we want to do is we want to find what the units of C are. Now, this can be a little just a short note on notation. The units of charge we call coulombs, and we give that a capital C. It was an unfortunate choice that when we say we want to talk about capacitance, we also use a capital C. So those quantities are not quite related to each other as directly as saying the units are the same, but just be careful that when you're talking about charge, you have a unit of a coulomb, which we give a capital C, and when we talk about capacitance, the derived unit is what's called a farad. So I want to see, based off of knowing what the unit of a charge is and knowing what the unit of electric potential is, what should the units of capacitance be? So go ahead and take a couple of minutes to try to figure that out. Go ahead and talk about this one. So we wanted to find what the units of capacitance are, and we know that from the equation that I gave you that Q is equal to V times C. So to rearrange this, C is equal to Q divided by V. Now we could take one approach to this and say, well, the units of V are volts, and then the units of Q are coulombs. So this is the same thing as saying that the units of C are coulombs per volt. But then we kind of introduce this volt here, which itself is a derived unit. And so what we would like to do is we like to get it all the way back to understanding how this can be related to a force or a potential energy, because we're familiar with newtons and joules and what those are made out of. So in order to go from force to electric potential, we had this table that showed us all the relationships between these quantities. And I could go across the top and then down here, or I could go from force to potential energy to voltage. So I'm going to actually just do this bottom step here. We know that potential energy has units of what? What are the units of energy? Joules, right? So this has a unit of a joule, and to get from, which is the same thing as a Newton times a meter, which is the same thing as a kilogram meter squared per second squared if you're into base units. Okay. So then to get from potential energy to electric potential was the same kind of way we went from force to electric field. So the force on a charged particle in the presence of an electric field is just equal to the charge times the electric field. The potential energy of an ensemble or a group of particles is going to be equal to the value of a particle in a potential times its charge. So U is equal to Q times V. And so that means to go from here to here, or to say what the units of V are, is to say that this is going to be a joule per coulomb, right? So then I can take this and I can bring it over here, and what that says is that the units of capacitance are going to be, take this V, put it in the denominator, that flips this, right? So that ends up being a coulomb squared per joule. Okay? All right, so let's look at some examples of this. So let's go ahead and talk about this one, and then we'll move on to something that's probably a little bit easier than finding this one, and that's doing the parallel system. Okay, so we want to find first what the charge, or sorry, what the charge is on each capacitor. Now, when capacitors are in series, the charge on each one of them is going to be the same, provided I didn't put some charge on the system to start with. So what that means is, if I reduce this system of capacitors in series to just one capacitor, then the charge on this equivalent capacitor is going to be the same as the charge that is on each one of these individual capacitors. So what we can do is we can calculate what CEQ is by saying that in series we can find the equivalent capacitance by saying 1 over CEQ is equal to 1 over C1 plus 1 over C2, which in this case is going to be equal to 1 over 12 microfarads plus 1 over 60 microfarads. 1 over 12 in 60ths is going to be 5 60ths, so we can make this 1 over 12 a 5 divided by 60. And then when we add these together, this gives us 6 over 60 microfarads. When I invert this, this ends up being 10 microfarads. So the equivalent capacitance here is going to be 10 microfarads. Now, in order to find what the charge is, now that I have this equivalent capacitance, what I can say is that the charge Q is going to be equal to the voltage times the equivalent capacitance. And so this is going to be equal to 10 volts times 10 microfarads, which is going to be equal to 100 microcoulombs. Okay, so that's what our charge is on each one of these individual capacitors. For the same reason that when I had resistors in series, if I found the current going through the equivalent resistor, that current is the same current that flows through each one of the individual resistors when they're in series. Okay, so the next thing that we wanted to find was what the voltage across each capacitor was. And so in order to do that, we know what the charge is on each one of these. We just say then that the voltage, V, is going to be equal to that charge divided by the capacitors. So the voltage across 1 is going to be Q divided by C1, which is going to be 100 microcoulombs divided by, was 112 or 60? 12 microfarads. Our micros are going to cancel, and so this ends up giving us numbers, right? So this is going to be 50 divided by, this is 25 thirds. 25 over 3 volts. Okay. Now we can do the same thing for the second one, right? So for the second one, we can say V2 is equal to Q divided by C2, and this is going to give us 100 microcoulombs divided by 60 microfarads, and this one is going to give us 5 thirds, right? Yeah, 5 thirds volts. And so what's interesting here is if I take this, it's required, if I take this and I add it to this, it gives me the same voltage that I inputted into the circuit. So 25 thirds plus 5 thirds is 30 thirds, 30 thirds is 10, right? So that gives us the voltage that I started with here, as it should. Okay, so to find what the energy stored in each capacitor is, you can take this equation that I have here. You can say that UC is equal to 1/2, appropriate for where we are, I guess, right? We have the variable UC. Okay. I'll let the laughter die down. So UC is equal to 1/2 Q squared divided by C, and so I can plug that in for each one of these, and what I end up finding is that the first one has an energy of 416 microjoules, and the second one has an energy of 83 microjoules. Okay? And that's it. So then the next one, we're running a little short on time. So this is, okay, it's T minus 5 minutes. Okay, so quickly do the same thing for if this is in parallel, and then I'll bring up the, well, you guys know what the question is. I don't want you to miss this after you guys asked me to put this on. I'm sure some of you would never forgive me if I didn't. So I'm going to put this back up, but the question is it's really the same question, only now now the capacitors are in parallel instead of in series. All right, so very quickly, because I'm running out of time, I got 1 minute and 40 seconds to do this for you guys. So what's different about this one, and what actually makes this one a little bit easier than the last one, is I don't even need to find what the equivalent capacitance is. I just need to draw 2 loops here. So call this loop A and loop B. So that will give me that V is equal to Q1 over C1 and V is equal to Q2 over C2. And then you can solve for your charges from there. Once you have your charges, you can do everything else. Okay, so I'll turn the sound on now. Some of you guys are panicking.